Welcome to the second paper session, exploring new and recent OpenMP extensions. So our first speaker, Jan Siesko from Sandia National Lab. He's going to be presenting his paper, Characterizing the Performance of Task Reductions in OpenMP 5.x Implementations.
Thank you, Deepak. Okay, so hello everybody in the room. Also hello to everybody who connected over Zoom. It's great having you here today. So my name is Jan Siesko. I'm with Sandia. I work mostly on basically as a dev in the Cocos core team. I work also on the user level threading libraries at Sandia. And recently I also started to work on the OMPI support of user level threading in that software. And I teamed up with Steven on this topic, and we had a common interest in this. Steven was, or both of us were interested to see what is the status of task parallel reductions nowadays in the community compilers, namely LLVM, Clang, and GCC. Then the other motivation was in Cocos, of course, we rely on abstractions in the underlying, on the backend implementations. And currently we don't have, we don't use task reduction. We don't even use parallel reduction. So we are interested in to see what the status is of reduction support, and if we can reuse the reduction clauses in, for example, Cocos or the last motivation was that I worked on this topic as part of my dissertation around 2013, 2015, and I, together with my colleagues and many of you, we proposed the task parallel reduction support around 2015 to the language committee. And at that time, it was relatively simple. We kind of had a broad idea of, okay, we need to define the scope. Okay, yes, because tasks fly around and we need to group them into something and define the scope. And then we also need to define the participating tasks. However, in the reference programming model that we use, everything is simpler. So I believe this is going to be a simple, straightforward thing to support while computable while loops. And it turned out the spec obtained some complexity on this topic. So I was really interested in taking a look at it in the current specification. What I prepared for you today is this agenda. So I have an intro slide on reductions. Then we will take a look at how LLVM implements reduction support with tasks. I have a list of benchmarks that we ported and that I would like to show you. We have an evaluation, of course, and a conclusion. So taking a look at reduction support shows that the support for reductions in OpenMP goes back to the version 1.0, where when I looked this up, I saw that it's a fantastically short document. It's a 60-page document that reads like a book. It's fantastic. And then when I scrolled through it and I looked at the 5.2 specification that has almost 600 pages, I saw what the current implementation or specification, in this case, or the implementation of the idea in the spec looks like. And this transition came about or was motivated with the introduction of tasking in version 3.0 in 2008, where we suddenly saw, okay, so if I can express an algorithm with tasks, can I somehow have these tasks contributed in reduction? And there are algorithms in combinatorics that really like to use this task parallel algorithmic formulation, especially when one has recursions. So there was a certain demand for task parallel reductions that I also picked up to work on because the topic of the thesis was such that we wanted to have this. And so I started working on this in 2013. We presented it to the language committee in 2015. It made it into the proposal in 2018 into 5.0. And today, task reductions are conceptually independent of the depend clause. So you program them completely independently. The reduction is more about about the data access. It's not about task scheduling per se. And finally, here I'm listing again that we are interested in seeing how what the degree of support is today in the mainline community compilers. The big additions, and this is one takeaway that I would like you to take with you, is that we basically added 4 constructs, basically 2 new that are completely new, which is the task underscore reduction and the in reduction, which many perhaps of you haven't seen. However, for the semantic value that these clauses have has changed for these 4 clauses. So now we have 4 new, semantically new clauses. The first one is the reduction clause. The reduction clause can be applied to parallel and work sharing constructs for section and scope. And the new thing here is that you are giving it an additional modifier. That's the first entry. That's the task modifier that says that the explicit tasks generated within that region will be tasks that collaborate or participate in a reduction. So the reduction clause with the task specifier or modifier, it represents a scoping and a participation construct or clause. Then we have a reduction without mentioning the task modifier, and that thing is applicable on task loops. So a task loop is a construct that creates explicit tasks, and it is similar as if you were to apply a task group with a task reduction clause. So it's a scoping and participation construct. Then we have a task underscore reduction clause that is applicable only on a task group. So here we don't create explicitly new participating tasks, but we define a scope. And we say everything inside that can happen, such as other tasks, can or may not participate in that reduction. And the final thing is a participation only clause, which is the in underscore reduction that can be applied to everything that looks like a task, basically the task, target task, and task group. And this allows us to stack tasks and associate them if we would like to, so we don't allocate every time memory if we create, for example, a recursion or a new recursive level. So the rule of thumb, if you ever write OpenMP programs, is you need a scope. So the participating tasks must have an enclosing scope that define the task parallel reduction, and then the reduction computation completes by the time the scope ends, or anywhere in between, somewhere. But you can rely on it when the thing ends. Now, of course, we tried as the first thing to take a Hello World app or a function here that takes some argument, a reference to it. So this is C++ code right now that you're looking at. You can see it in the first rectangle in the first code section. And then we compute a task parallel reduction over that some variable. Here you can see I'm using the task group, so we will scope that task in a task group context. We mark it as a task reduction. We reuse the same operator, so this is the built-in operator, and the sum. And then we give it the name, the list item in this case, which is the sum that we are passing as a reference, and then we increment it. And now we looked, of course, at both what GCC in the both in the latest versions. I snapshotted this in I think in June or something like that. And we can look at the GCC generated code and the Clang. Of course, the Clang generated code is complex because the intermediate representation makes it complex and is not so nice to read. The GCC intermediate code looks very nicely. And what we see is we have the original function. So that's the user provided function. Then we outline the task body. We pass the arguments to the task body. So these are those arguments that are implicitly or explicitly captured by the task clause. And then what happens inside is relatively nice, and it's good to see. So we see privatization. And for this purpose, we create a double pointer. Then we assign the inner pointer to the original memory location. So in case we participate in another reduction, this points to that memory of that outer scope of that reduction where we participated. So the inner scope is now the task. The outer scope is some memory. We don't care right now which one, where the original item was allocated. Then further later down here, we assign that we dereference once the pointer. So you see we dereference once. We assign a pointer to that original list item location to that inner pointer to the dereference pointer, and we pass this to the task reduction remap. And this can, or in this case, it does allocate or request, or basically, let me correct this, it looks up in a hash map which is the participating reduction for this list item. So that's why we need a pointer to the memory location, and then requests the thread private storage for that list item. Okay, so we get that, fine. So we have it down here. We dereference twice. You see it in lines 15 and 16, and we perform the arithmetic operation here, and we are done. So it's good to see that we have per thread privatization, even for tasks. This is what we basically expected, because this ensures we have potentially the lowest overhead. We reuse data as much as possible, and we use privatization, which typically is an approach that likely scaled best compared to atomics. Good. Now, we also prepared a set of benchmarks. For this purpose, we created yet another task bench suite, the OMP task bench. The OMP task bench will include some more specialty benchmarks also around the detach clause, etc. that we are planning. Right now, it has only one subdirectory. It's called reductions. And then there we have a bunch of combinatorial problems that are being solved by these modules. So it's a CMake project. It's trivial to compile and run. And we selected 4 applications for this evaluation. We have fib, we have PowerSet. PowerSet basically calculates the permutations of the number n, so it's a factorial. We have the same thing with the UDR, where the type of the reduction object is static, but it varies in size. So we would see the cost of allocating over, larger memories or data types. And then we have dot product. The difference is that fib and PowerSet are recursive, and dot product is iterative. The dot product, I give it a vector and I receive a scalar back. So it's also very easy to parallelize. Okay, so I have a couple of implementations that I wanted to show you. The first one uses the parallel reduction construct that takes the task specifier and then the operator and sum. And you can see that here in the gray rectangle, I have basically the main code, what is in the main method, and then I have the function, which is called recursive in the orange box. So it's quite a typical implementation as you would expect. So I refer to this implementation in the evaluation section as parallel minus red, parallel red. I have the same thing called task group red. Okay, this is how I'm going to refer to it in the task group, in the evaluation. So we have a task group reduction. So it uses parallel construct, but without the reduction, and I have a single construct. So one thread enters here. I have a task group with a task reduction clause on it, as we discussed previously. Then I create the first task, an explicit task, and then the inner body of the task here in the orange box creates these recursive levels and creates a gigantic amount of tasks, insane amount of tasks, as we will see later on. Then I have a version called the stack. So many of these algorithms can be formulated in a way where I, at each recursive level, create a new stack variable and give it to the task to work on. So I don't need to protect any accesses. I don't need to be smart about how I access memory, because I give it stack local variables every time on each recursive level. However, in order to not run out of the stack before the inner tasks compute that reference that memory, or where I need the result, even though they don't reference it because we pass by value on the stack, but still I need to wait for the results of the inner task. So I need to have a task wait. Okay, and this is a task scheduling point which has implications on the performance, as we will see later. So I have a task wait here, and I refer to it as the stack implementation. Then I have one version that uses the thread private clause. So I'm not relying on reduction support at all. This code doesn't mention reduction, but it has a thread private scope, basically annotating the task function. So everything in this task function, all accesses to the variables will be redirected to the thread private variable, and the redirection will happens by the as the compiler generates the redirection, replaces the occurrences of the list item. Now let's move on to evaluation. So these were the implementations that I showed you for fib. They're somewhat similar to PowerSet. I think it's not necessary to take a look at them, and dot product is also quite obvious. So we tried on a system that looks like this. So it's a Xeon with 48 cores with a bunch of RAM in it. We use these flags. We use these environment options. So when we scale the number of threads, we increment the thread ID by 1, and the next thread is always the closest to the previous one. We are not using the hyperthread cores. And then I'm using LLVM Clang in the version 14. This is the official release. It's the version 14. And GCC 13, I cloned the repo and built it in May. Okay, that's a version from May. And the methodology, I ran all the benchmarks 5 times. I took the average time. I plotted the standard deviation. I tried very large task counts that are unreasonably large simply to accumulate the overheads and to see something. Of course, overheads can be relatively small if we create a reasonable number of tasks and use, for example, the final clause in order to implement the cutoff over the task generation. Now, the downside is that we are blending together overheads coming from tasking and reductions, and keeping them apart is difficult, and the evaluation section requires quite some interpretation to understand what we are seeing. Okay, so this is my first evaluation slide where we are taking a look at Fibonacci. And what you are seeing here are 2 graphs. On the left-hand side, we have the performance results obtained from a binary compiled with the LLVM Clang compiler. On the right-hand side, we have the binary obtained with the GCC G++ compiler. And you see that we are measuring the time of execution, so the lower the better, over the number of tasks. So here we create for a specific problem set. So the problem size is the same. It's a Fibonacci over the number 33, whatever that is. We create 1,200 tasks to 11 million tasks. So it's quite a substantial number of tasks in order to accumulate the overheads and see, expose these overheads and be able to compare something. And what you can see is that we have different charts, so different chart lines, and these correspond to the different implementations. For example, we have a blue line that corresponds to the stack implementation, where we use the stack and we use the task weight on each recursive level in order to wait for the inner computation. And you see that there is a column of different implementations that correspond to the different colors. Now, taking a broad view at these both graphs show that overheads typically are lower for the smaller number of tasks. So the further right you go in both, the worse things become. Now, we see that Clang generated the lowest overhead when there is no reduction at all. Okay, so that's the blue line on the left-hand side, noted with the letter number 1. Now, interestingly, for GCC G++, when we drop in the task weight, it results in the highest overheads further to the right, as you can see on the right-hand side, side graph, where the task weight impacts performance for GCC and G++ the most, which is an interesting consideration. And even though this deserves more evaluation, it is likely that this is related how the task queues are implemented, and especially how many we have. Very good. Okay, then we have an implementation that is called thread private. So here, the thread private implementation uses OMP thread private. But of course, here the important thing is, so that's the orange line here in both cases. If I use manually privatized variables through the OMP thread private construct, then I need an extra loop later on to reduce them by myself, right, into the results. So once the computation is done, I have 48 temporal variables that correspond to 48 threads, but I need to have another loop that reduces them. So this is visible here for the low task counts. The extra for loop that I have to create, even if it's in the same parallel region, creates an additional time that is shown here. And that's why we have that orange line being higher for those smaller task counts. And then taking a look at all the other approaches, basically the different green shades, we see that they fall more or less into the same kind of trend line. So they could be grouped together. They coincide pretty well. And the difference is likely between these two compilers is the cost of tasking in general and the cost of the hash map lookup. And it would require to detail this further, but this was not the objective of this work, to understand maybe potentially these performance differences in that detail. We have the power set benchmark that also creates a gigantic number of tasks. Both task graphs are relatively even, so they are not degenerated in any direction. Here we create a smaller range, so we can study another range of tasks. So we created here 2 to 265K tasks. And we see that for a reasonable number of tasks, that is for the task numbers that correspond to the degree of concurrency to the number of threads that we are giving it, all the techniques more or less coincide. There is one outlier that is always present, which is the atomic implementation. The atomic implementation suffers from resource contention. So that was as expected. We see again that the stack implementation differs, especially towards the right sides of the chart. Again, the same issue like in the previous, it's related to the task weights. And then we see that for an increasing number of tasks, the task group and the task group implementation diverge. And this is interesting, and again, is an indication that the cost of tasking and the cost of hash map lookup is different for these two implementations on these two compilers. Now, before I switch to UDR, so basically the next slide that I have is when we take a fixed number of tasks. So basically we look for a spot on the horizontal axis, on the x-axis. So we look for a number of tasks and keep everything the same. So here we will take 265K tasks. So it's the chart. It's basically a vertical line that would correspond to the rightmost number of tasks, and take a closer look what happens. So here I'm taking a fixed number of tasks, 262K tasks, and I now vary the size of the target of the reduction variable. So I created a whole bunch of binaries. So this is statically allocated. It's a UDR type. So it's a statically non-compile time known type, where I implemented the user-defined reduction, so the reducer and the initializer for this. And what we can see is that the stack implementation differs. Okay, so here again we see the same behavior like we saw previously for GCC, the version with the stack that uses the stack for the variables takes longest, so it has the lowest performance. So that's a theme that repeats itself. Interestingly, on the left-hand side for Clang, when we use the stack implementation, where the overheads are significantly lower, we see an effect that turns out to be caching effects from jumping through the stack in big steps. And we see that when we increase the size of the reduction variable, the performance degrades. And this is the line, the blue line, which is marked by the circle number 1. And then I have the last evaluation chart here, which shows the dot product. And the dot product is not recursive. So I can also use, for example, parallel 4 without any tasking. And that exactly corresponds to the line number 1. So without any tasking, if I only use parallel 4, then we don't rely on the number of tasks. So we have a flat line. That's the orange line. And then everything other than that supports the story that I mentioned previously. So when we reach a degree of concurrency here with, for example, 48 or 100 tasks, then the performance kind of reaches its best level. And then further to the left or further to the right, we see again the overheads of the hash map, lookup, the access to the queues, etc. So what is the conclusion of this talk? So we have to say that both compilers support task parallel reductions as it's specified, as it's in the current spec. The performance is comparable across the different modes of expressing task parallel reductions. For large task counts, we see overheads. Overheads because tasking has its cost and requires queue operations, as well as we have the task variable lookup in order to associate list elements with the given scope. And we recommend the use of these constructs. To us, it seems that the endeavor that we started 2015 was fruitful, that the constructs are useful, that I think readers and implementers got the ideas right of scoping and participation. So we were happy to see that. And we look forward to add this also to our abstraction programming libraries that we have. And potentially we are looking at future work where we would like to take a closer look at the tasking performance, because I mentioned it a lot during my talk, but I didn't give you an explanation that would be good enough. Thank you.
Okay, we'll take some questions in the room first, and then we'll go online.
Thanks for the talk. On your evaluation slides, if you go back, one more. Here, this is good. The next one is better. Let's start here. Is this on the left side? There's this long stretch where the number of tasks increases, but our time basically stagnates, right? It's like a line, more or less, for a long time. Doesn't that mean that our bottleneck is somewhere else and the number of tasks doesn't actually matter? So we have something there that is kind of the same costs always, and whatever scales with the number of tasks is basically free?
It shouldn't be probably free because we see a change in the line over the number of tasks. So there is a correlation.
Okay, it's not free, but compared to the fixed cost of whatever the rest is.
Yes, potentially. However, in this case, you are looking at a task range ranging from one task. Perhaps you haven't noticed that here in the horizontal axis, we start from 2 tasks and we go up to the number of 265K. This is different to the previous scale where we used, I flipped just for a second. So we started here with 1,000 and went up to 11 million.
Okay.
Here the range is smaller, and for the left-hand side, we don't simply have the degree of concurrency there on the left-hand side. Then we have, you see, for the number of, for 2 tasks, you spend a lot of time in 2 tasks.
Okay, that's fair. But let's look at the 10 to the power 3 to 10 to the power 4. You should have sufficient concurrency there, right? It's like between what?
Yeah. Okay. So you are asking why the flat line here?
It's still flat enough for me, and given that we,
I think the explanation here is that we are increasing the degree of concurrency. That's one effect. Even though we have 48 threads, but the overheads grow, so we counterbalance the benefits of having more concurrency with the growing overheads. And they flatten out at some point. So you have that time where one improves, but the other one degrades, and then the other one degrades more and more and more and more, and so you grow.
Okay,
but good consideration. But I think it's a factor in the function of overhead. It's the number of tasks.
That's good.
Any questions online?
Just one, and I didn't understand what you meant by the size of the variable. You had a plot in there, size of the reduction variable. Was that the number of total iterations or additions you do someplace? What do you mean by that?
Yes, so thank you for the question. So when you program reductions in OpenMP, you have a possibility to define a user-defined reduction. And the user-defined reduction requires three things. First, you give it a reduction variable, and this variable is of some type. It can be an integer, it can be a double, it can be any user-defined type. For example, it can be a struct. It can be a struct of 2 doubles. It can be a struct of 128 doubles. It can be whatever you give it.
Oh, okay, good. That's thank you.
Of course, the allocation size is then equivalent to the size of that type.
Okay,
Abed has his hand up.
is there another comment?
I was just saying, Abed has his hand up politely, waiting to be called on.
Yeah. Thank you. Thank you for pointing. Well, I have one question. Like you use one variable like thread pinning, like a close. I think that's one variable you use in your experimentation. Number one, does it affect the study like execution time, like when you pin to a socket or very close? Number one, and number two, do you think data locality could be a variable in this study?
So to answer your first question, if we looked at pinning and giving it different environmental variables, yes, it affects performance. However, I don't have it in my mind anymore what happens if the creation of threads and the pinning to the threads correspond or prioritizes by core. So we would basically create ascending thread IDs that would correspond to core number 1 and then core number 25 and then core number 2 and then 26 and so on. I forgot what the performance characteristic was, but I believe it was nothing that would add to the story, so I dropped it. And the last question that you had, I think I forgot what it was. Would you mind?
It was about data locality. Data locality.
Can you say that one more time?
It's about data locality as a does it affect this performance?
So data locality always affects performance. However, in this case, data locality is given because we privatize per thread. That means that every task that is created, it accesses that data on that given, let's say, socket or on that given group that correspond to a cache in the cache hierarchy. So we expect that the locality is given because we reuse the data. However, for example, in the implementation that uses stack, that means we allocate potentially big pieces of data depending on the user-defined type. We see that we jump through memory relatively quickly. If every stack operation needs to allocate 131 kilobyte of data, then we advance the stack pointer relatively quickly, where we see then caching effects, especially for those large numbers of tasks.
Thank you.
You're welcome.
Any other questions? Okay, I have one question. So given the differences you're observing between LLVM and GCC, are there any general recommendations you would have for users who are using the task reduction feature that you would say generally would work well across different implementations? And maybe what are some specific ways in which you would suggest they not use it?
Yes, so typically when somebody writes a Perl program, he wants to get things done quickly, and one opens up maybe the OpenMP spec or not, but one could also think of manually implementing reductions. And there are two ways: either I privatize manually by myself and add a bunch of code with memory allocations that I need to handle, or I want to use atomics because we have that in OpenMP, so I can do Pragma OMP atomic and then have that. However, it results in bad performance. So as always, it's good to read the spec occasionally or include, teaching about OpenMP features in courses and lectures and workshops in order to for the users to have knowledge about these constructs. And then which construct in particular they use, if it's a task loop or a task group, depends on the use case. So they both have different meanings and different use cases. And we see comparable performance across both of them. And we are positive that the testing efficiencies will be polished, and it's a trend that shouldn't shouldn't go into a negative direction. So we are very, very positive that the performance will be competitive and that it pays off to use these abstractions that the programming model is giving you.
Okay, thank you. So let's thank the speaker. Sure.
I was wondering, you used affinity and proc-bind close and OMP places cores, and considering its tasking, and the task could be any place. Were there any differences in the performance with the close or the spread or anything with affinity, or was it pretty much consistent no matter how it was set up?
Thanks for the question. Yeah, we saw differences. I remember that together with Steven, we tried with a different affinity clauses, especially because I forgot to put them in, and he told me later on, "Did you put them in?" And no, I didn't. I forgot. And I remember that firstly we saw large differences between the default behavior on Clang and GCC. And yeah. And,
which means leave it open to run any place, and then the other one was sort of confine it. Okay.
Yeah, exactly. So then by specifying the environment variables and pin the threads and use the locality features, OpenMP made this much more consistent. So so in other words, it's important and don't rely on the default affinity behavior.
Yeah, we've found that too. So that's a good confirmation. Thank you.
Mm-hmm.
So this is Helen. By default, if you don't specify versus if you say OMP proc-bind equals true, would true be better than not specify? And how do you compare performance between true versus spread or close? This is like in general, not just for the applications in this talk.
Shouldn't true be implementation defined, but then if you specify close and cores, then of course you're being more specific. And if you don't say anything, then the kernel just allows it to run on any of the cores. That's my general opinion.
Yeah, so true does bind. If you don't say true, I don't know if the default is false or what. It's also implementation defined, right? And if you do spread or close that you're controlling, I just want to. So
yeah, I mean,
the thing is that how do we say? When you say true, it could be spread, it could be bind. I'm just trying to say if implementations would see you say true and help you to find whether in your application it's better to spread, it's better to close, and
so Helen, my experience
true
is
would
that
actually give you best options for if you using different compilers and without changing your specification to spread or close. Also depending on whether you're subscribing or oversubscribing using hyperthread or not.
So my experience is that the implementations do something sane with true, but I don't think I would rely on it lest some rogue implementation decide to do something stupid. I mean, my experience is that the major ones do, something reasonable, which is like if you're using a number of threads equal to number of cores, it puts them all on those cores. But, there's nothing that would stop an implementation from, say, packing them all into the first few cores with multiple hyperthreads per core and leaving some cores with no work on them. I mean, that would be valid. So that's why I would say people, I mean, yeah, I see what you're saying, that you could try true to see if it works well, and maybe it does. And I've seen most implementations do seem to do pretty well with that and not do something stupid, but I'd be weary for portability.
In principle, you could always check with display affinity what the pinning or binding is, but I would also say that it's preferable, the best option to be precise and say coarse close or coarse spread.
So with Cocos, actually, if you run Cocos with its OpenMP backend and you don't specify the binding, it prints out a nasty warning message telling you, we really recommend that you set these bindings. Something bad may be happening here. And just so users know that they need to pay attention to that.
I think it was probably from a couple of years ago, and when we using spread more than true, and maybe one of the compilers was not giving the optimal binding. So it seems like true is more overall the compiler is doing the right thing, at least not putting all the cores threads on the first few cores. They are either spread or close, depending on your how many tasks or threads you're using for your application. So
it also
maybe
depends on the application. So if the application does heavy communication or needs to exchange data between neighboring threads or something, then close might be a better option than spread. But if your application is highly memory bound, you want to use spread, I think.
Yeah, it is.
But I've also seen some bugs in for example, LLVM, where you say, okay, for example, we have a machine with subnumber clustering. And if you say spread, then depending, so if, for example, I did some scaling experiments, it does not spread out the threads in the correct manner, how I would assume it. And then there's also a bug report about that, but I think this not has been fixed. So there's a workaround for that, but I always recommend to check how the binding is with display affinity or KMP affinity, depending on what you use.
Yeah, we do tell users to check the bindings with display affinity, or we also have a in-house code that actually adapted from HPE's original code to display hybrid MP OpenMP. So it's not just display affinity giving you the OpenMP thread affinity. There's also related, I think the affinity from process affinity and the thread affinity is also related to the batch scheduler we have, and also whether the number of process MPI tasks is divisible by number of cores on a node. Like for Kernel, it was 68 cores. It's really not even divisible by normal usage of how many tasks you want. Yeah, I think depending on how many tasks and threads you use, it's sometimes better with spread, sometimes with close. My question is, would setting to true, be how reliable is true to give you the spread or close performance? It actually knows that you want close, you want spread.
I don't know. I wouldn't. True. I wouldn't rely on true at all. So setting it to true does not tell you anything. It says it binds the threads, but
yeah, it says
it does not tell you more. So,
well, not only that, but I mean, by that same token, right? If you feel like the implementation should know what's pretty much the right thing to do, I feel like most implementations, even if you put proc bind equals false or don't specify anything at all, then they should pin, because pinning's usually helpful. So they have that, they could do that as well.
I've always found it's good to not even trust yourself, but to use a tool that explains or shows you the affinity that's being used, where the cores are being set, and actually where they can run. And so there are various tools out there to do that. And I've found that extremely helpful because lots of times you think you know how you're setting the affinity in the more complicated cases, but it's not being set to that. And so it's always good to do a check.
Yeah, we have the application says putting this our provided binary already compiled, just replace with your real application, and this will tell you your affinity setting.
Yeah, we have some tools like that. AMask, we have one that you can just connect to where your job's running, and it will show you where it's running. You know, how the occupation and actually where it's allowed to run. So those are good things when you get serious about it to have around to check those out first to say, check me out. Is this, I'm trying to set the affinity special, and am I really getting that?
My original question was to ask the vendors how much implementation or detail you put into the proc binary equals true, and what do you do things differently, whether it's so I think what I get from is don't trust true much as your own control.
Well, it also depends on how many threads. It depends on how many threads you're making, right? I mean, so if you're using a number of threads equal to number of cores, which is a lot of times what folks kind of do by default, true will often put one per core, and that's probably what you're looking for. If you have a different number of threads than you have number of cores or number of hyperthreads, then you may get interesting configurations that might not be what you want.
Good point.
And I agree, Kent, don't trust yourself.
Say you have.
I know myself too well, and that's why I don't trust myself.
So if you have 4 cores and you only want 2 threads, and then I think spread will spread them out. And if you do true, it'll do the 2, and without using hyperthreading. If you use close, it'll put it on 1 core with 2 hyperthreads, right? So true would say if you have 4 physical cores and 2 hyperthreads each, and if you want 2 threads only, and spread will put them on core 0 and core 2 maybe. And
well, the question is, what do
true
you want?
Will put on
right?
0 and 1, and close would put both of them on 0 with 2 hyperthreads.
Well, it depends on how you define your places, right? But
places equals
thread. If you think about a scenario where you have 2 sockets, right? It doesn't necessarily know whether you'd benefit from having if you just have a couple of threads or something and you have a bunch of cores on each of the sockets, it doesn't really know if you would benefit from having those on the same socket because they're going to use the same memory, or if they'd be better off being on the 2 different sockets because that way you maximize the memory bandwidth available on the board. So I don't know how we can expect a vendor to know which one you want.
So I'm already doing MPI, and I'm putting MPI. So MPI already multiple MPIs. How do we say? There's no MPI.
You have multiple
both sockets. Yeah, I'm already using multiple processes.
Yeah.
So my MPI task is already on 1 socket, and then on top of that, it's using OpenMP. So it's within 1 thread, and we usually put places equals threads, and then we know they're hyperthreads. So I'm trying to distinguish true versus spread versus close, right?
Yeah, I mean, true just binds to something. Yeah. If it's implemented sensibly, it will bind spread because, well, spread, assuming it's implemented according to the cache hierarchy, and you give the largest subsegment of cache to each thread that you can and bind to that is what users want 99.999% of the time. Now that remainder, it really, really matters for that remainder, but there aren't very many of them, right? So I would be very
right, but depending on the architecture, I mean, so Alan, what you're saying about the sockets, but let's say you're on a KNL, you've got a bunch of tiles, right? And the tiles share a cache. Do you want them to be using the same cache? competing
That's
for it or
exactly the
potentially
point.
sharing it, or
If-
do you want
If
to
you
have
used
them
up
using
all the
separate?
hyperthreads, you would have to. But if not, we try to spread them out. Or true, if you're not using hyperthread, true, whether you really spread them out or if you're already putting one thread on each core, that should be not too bad. Yeah, I know you two cores sharing one level of cache on the KNL, so you actually want them spread is better. Otherwise,
Yeah, but it isn't.
true is good enough.
It depends entirely on what the application is. If you have something that's cache bound, then yeah, you might want just one per core pair. There's the same thing on a Sierra-like system.
Uh-huh.
But on all of these, the most likely thing to work for the average application is spread, full stop. Because it actually gives you as much independent cache as is reasonable. So if anything does anything other than that for true, I would be vaguely shocked and probably file a bug report. But for the other cases, it's entirely application dependent. Right? You might want clubs. You might want round robin to cross sockets because you're actually communicating on a stride or something. It's impossible to know without looking at a specific application.
You said in general you recommend spread.
Yes.
Mhm.
By a mile.
Yeah, it was I think a couple of years back when we tried spread with at least one of the compilers. Maybe it's because due to a bug, spread is not good as true. Doing the wrong thing at that point. So when we try to give a overall recommendation that across compilers, and we decide to use true.
What I do find missing, and this is sort of crossover between MPI and OpenMP, is that when you run an MPI executable, an application, you can only specify one OpenMP type of configuration for all the different processes in MPI. And it would be nice, this is probably the 0.01% for cases where you want a different affinity for the different MPI processes.
But you can already do that, Ken.
You can, but it's difficult. It's not trivial.
You put env in front of your executable, use different ranks, but it's
yes,
hard.
the ranks. You can do that, but it's not
or with
very
the script.
simple. Yeah,
and
with
you
the
don't do
script.
executable, you just run your script.
Exactly.
Well, at one point there was a proposal for routines that would allow you to set affinity and not just get it. And you could, of course, call those from the different ranks if we had that capability. But I think we decided that might not be a good idea.
And actually, I would note, Ken, some of the MPI runners have direct support for specifying environment variables on a per rank basis or separate commands. So check with your resource manager or MPI runner, and you may find better resources.
Oh, good. Thank you, Tom.
Do you use attack? Ken, what resource manager do you use attack?
Slurm. All over the place.
I was going to say, it wouldn't surprise me.
I can't hear you, Bronis.
Are you going to say he
Tom's
should
answer
use
was
Flux?
that Slurm provides it, but with some difficulty.
Okay, thanks.
It's Slurm.
So Abid has put in the chat something about next talk is at 10:30 a.m. But what happened to the talk we were supposed to have just had? Is it just
Yeah, we just had that talk.
Okay.
Yeah, unfortunately, the speaker didn't show up. So we're going to go ahead and take our break now, and we'll resume past the hour.
All right. Thanks.